Hello, good morning, everyone. In our last lecture, we have discussed CSMACD, that is Carrier Sense Multiple Access Collision Detection. And we have seen that in the link layer, a host must transmit at least till the duration which is greater than or equal to twice the propagation delay. Because if the transmission time of a host for a packet is less than twice the propagation delay, then it may not be able to detect collision. Ethernet is one such protocol that uses CSMACD. That's what we'll discuss today. Then we will look at layer 2 switching. That is how different Ethernet segments or the host are connected to a device. Even though we say Ethernet limits the collision domain, can we further segregate it? And that is the concept of called virtual lens or VLANs. And lastly, we would discuss flooding or broadcast store. That is, if we have layer 2 switches and if they are connected in a loop, then we might get into a problem leading to flooding or broadcast store. So let's start. Ethernet, when it started in late 70s, it was originated at Xerox. Later on, it is used to call DIX Ethernet, Digital Intel Xerox. Ethernet was initially a cable, coaxial cable, onto which a number of hosts would basically connect using a device called transceiver. First implementation of Ethernet was also known as 10 base 5. That basically means baseband bandwidth is 10 megabits per second and phi indicates 500 meter length. So one cable can at most be 500 meter length, onto which using transceivers they'll be connected. Transceiver is a device that will enable host to transmit and receive packet. It was too bulky to heavy a cable, so we got a lightweight cable which was called thin Ethernet. Original Ethernet also used to call thick Ethernet, but it was a very heavy cable, coaxial cable. And this thin Ethernet cable length was limited to 185 meters. So it was called 10 base 2. Then Ethernet moved from physical bus topology to actually what is called star topology, where a central device or a hub where device gets connected, like your central device. And this was connected using twisted pair cables. So that it called 10 base T. 10 is 10 megabits per second. T is twisted pair. Ethernet continued to evolve. Next speed evolution was 100 base T, that is 100 megabits Ethernet, which also called fast Ethernet. Then we also have Ethernet based on fiber. It became 100 base FX, indicating fast Ethernet over fiber. Then it evolved even to 1000 megabits, which is gigabit Ethernet. Then with 25 gigabit Ethernet, 40, and we have, it continues to evolve. So in today's Ethernet, we do not see a actual coaxial cable. All Ethernet deployments are primarily switch based. So you have a switch, which is called layer 2 switch. You can find a 4-port switch, 8-port switch, 24-port, or depending on how many configurations you would like to have. So in today's Ethernet, what we call switch Ethernet, we have a device which is layer 2 device. Onto each port, a host is connected. The benefit this switch-based technology gives, or the hub-based technology gave, versus the coaxial-based cable, the major problem with coaxial cable was if I need to add another station, we need to be putting a hole or cutting the cable, adding the transceiver, and that network would go down. Or anybody in the premises, if it plays with the cable, can break the cable and whole network would go down. In the hub-based setup, hub will be centralized in a closet. So if somebody disturbs the PC, switch automatically will bypass that ports and it will continue to work. And that's why the switch-based Ethernet is being used today. Now in today's deployment, each connectivity, each port between switch and the machine is a separate collision domain. That means between each line, between switch and the machine, we have what is called Ethernet running CSMA domain. And because we have only one station now, hence there is no collision per se that can occur, because collision would occur between two devices and we only one device. Of course, it is full Ethernet. That means a machine could be sending packet as well as receiving from the switch, but this being a full duplex. So typical cable, if you look at RJ45 cable, it has 8 cores. So 2 cores are used for transmitting from host to the switch, and another 2 core of the 8 core cable is switched to the host, and hence there is no collision. So in today's switch-based deployment, we do not see any collision per se at all. So let's look at, given that basic understanding of Ethernet, how does a frame look like? Now Ethernet machines are connected. It follows CSMA CD protocol. There is no clock synchronization. So when a host needs to transmit a packet, now each bit is represented in the media by a voltage level if it is copper cable. Now to understand how long the bit duration is, a receiver needs to have some clock synchronization. So Ethernet frame starts with a preamble, which is 7-byte preamble, sequence of ones and zeros, followed by a start frame delimiter, which is 8 bytes, which is not counted really in Ethernet frame. And this preamble enables a receiver to synchronize the clock. Then the first field in the Ethernet frame is destination MAC address. MAC address is 6 byte. And as we discussed in earlier classes, first 3 bytes correspond to organization ID and last 3 bytes organization allocates, and this MAC address is globally unique. So first field is destination address, 6 byte. Second field is source address, that is MAC address of the source. And you'll probably see that this is kind of different from the segment structure we have seen for IP or even TCP. In IP packet, we find source address first, then the destination. Even in TCP and UDP, we find source port first, destination port next field. But in Ethernet, it is the destination MAC address which is first, and then the source address which is the second field. The primary reason for this was when Ethernet started with this switch mode, it could have been called cut-through switching. That means typically the switch today, when we'll discuss in the next slides, when a host transmits a frame, switch receives the entire frame and does error checking and then only forwards to respective other links or other host. In cut-through switching, it can read the destination MAC address, and without waiting for receiving the entire frame, it can send out the frame. And that being the case, if destination MAC address was the second field, it would have to wait that much longer, 6 more bytes to read. So why to have the delay? And that's the one reason destination MAC address happened to be the first one. The next field is a type, which is 2 bytes, which basically indicates the high layer protocol. Later on, it evolved to indicate a length. So that means if any value, because frame size is maximum one would be 1536. So length value, if value happens to be less than decimal 1536, it is considered a length field. If value is more, is considered type. Like for indicating high layer protocol, that high layer is IP, value would be X800, that is 0x800. For ARP protocol, it will be 806, and so on, so forth. When networking started, there were a number of different networking stacks, like Novel Netware, which is IPX, AppleTalk, DECnet, XeroxNet. So indicating is an Ethernet was used by all. So to indicate what kind of high layer protocols were, with the type field to indicate the same. Then we have CRC, which we discussed in last class, which is primarily used for error checking. It is a 4-byte field. That means you have a generator, will take the entire frame starting from destination address till the data payload, compute CRC, and append that field. And receiver would basically check whether the frame is corrupted or not by computing its own CRC value, compares, and the two matches, then no frame is intact, and it will be delivered to the CPU by the network driver. Ethernet frame minimum size is 64 bytes, or precisely called octets, 8 bits. That means 64 into 8 is 512 bits. If your data payload is less than that, as you can see, the header size of a 6 byte of destination MAC, 6 byte of source, 2 byte for type, and 4 byte for CRC. So 4 plus 2 plus 6 plus 6 makes it 18. So 18 bytes of header overhead and a 1500 bytes of data, that make maximum size of 1518 bytes or an octet. If frame size is less, then there will be fuller field that will be involved. That means in Ethernet frame, maximum payload that can occur is 1500 octets. And if you want to look at, if you look at your machine like Linux or Windows, you can actually see what is the Ethernet payload size is. This will be indicated by MTU. So let me see if I can show you that. If I were to run link so device ENS160, which is the Ethernet interface, you see a field MTU 1500. This basically indicates that Ethernet frame size is 1500 bytes. That's for the payload part of it. Given that the Ethernet is, so host sends a packet, receiver will receive it, and minimum packet size of 64 bytes ensures that if collision were to occur, source would know the collision, and if collision occurs, it will stop and retransmit. And using the exponential binary backoff, which we discussed in last class, is going to retransmit a packet. If, however, sending host detects that there is no collision, it assumes packet is transmitted successfully. There is no connection setup between sending and the receiver. There is no handshake that occurs, and in that way Ethernet is connectionless. Some people say Ethernet is unreliable. It does not mean that packets are delivered corrupted. All it means is there is no ACK acknowledgement or negative ACK by the receiver to the sender saying we have received the frame or not received the frame. When frames are delivered, it assumes they are successfully delivered, and if reliability is needed in this sense that delivery acknowledgement has to come, then the high layer protocol like TCP, which we discussed while discussing TCP, reliable data transport, they have to have their own act mechanism to make sure packets are delivered and received. So but from Ethernet perspective, if sender detects no collision, it assumes packet is delivered and will not the, do any other action on that. As already said, Ethernet is unslotted CSMACD with binary backoff. That means it looks for a collision. If occurs, it stops it, retransmits it, wait for a time. If collision occurs again, it will choose a number between 0 to 2 raised to m minus 1, as we discussed in exponential binary backup algorithm, and that is the way the Ethernet delivery works. Now we look at how does a machine or a host sends packet to another machine when it is connected via a switch. Ethernet switch is primarily a layer 2 device that connects different segments. The way the layer 2 device works, when a host sends a frame, it receives the frame. When it receives the frame fully, does the error checking, make sure CRC is fine, and then only it will forward the frame to other host on the machine. And we will look at what is the logic that is used to forward the frame onto the other segments. The beauty of Ethernet connectivity is that when we add switches into the segment, a given host remains transparent to it. So whether you add one switch or two switch or other number of switches to add more number of hosts, let's say you got a 8-port switch, that means you can connect within a segment only 8 ports. But if you want to extend it, you can take one port and connect another switch with that port. So hosts do not have to be configured that there are more switches there and all the switches works in a transparent way. And in that sense, Ethernet switch is called plug and play device. They automatically learn the MAC addresses of the host, and using the MAC addresses they deliver, and that is what we'll basically discuss. They are plug and play in the sense that these do not need to be require any configuration. Against the router, when we use a router, we have to assign the IP addresses. For each interface, we have to configure the IP addresses and so on and so forth. But in Ethernet switches, we just connect, power it on, and no other configuration required in a typical Ethernet switch. So let's take a simple case of the connectivity. Consider we have a switch which has 6 ports and there are 6 stations are connected: host A, B, C, host A prime, B prime, and C prime. Now, as you said, each of the port connectivity with host is a dedicated segment that is this own collision domain. That basically means because in each Ethernet segment there is only one host, that means there will be in today's switch based implementation there is no collision. When a host sends a packet, switch would receive the packet, buffers it, and send it out. And said again it is full duplex. That means host A can transmit as well as it can receive packet at the same time, and that's the way Ethernet typically works. Now with this connectivity, it enables that A can transmit to A prime, B can transmit to B prime, C can transmit to C prime concurrently at the same time. And that is what the switch architecture enables. If it was a single coaxial cable based technology, if A is transmitting to A prime, no other device could have transmitted because that would have caused collision. So in that sense, using switches gives you much more higher throughput than what would have seen otherwise typically in a coaxial network. So we'll explore how does the switch works and what is the logic it uses to deliver. Primarily when A sends to A prime, how does switch know A prime is connected on this port number 4? Or when B sends to B prime, how does switch know that B prime is connected to 5? Buffering is also required. Let's say the two machines, both A sends to A prime and C also sends to A prime, then one packet will be transmitted, other would be buffered, and that will be sent out in the next turn. So in that sense, their collision would occur, but you cannot see that both A and C can do simultaneously. So they will receive, one of them would be buffered, it will be queued, and next packet would be sent to the machine in that sense. Now the question is, how does a host A knows, sorry, how does a switch knows that A is connected on port 1, B is connected on port 2, and so on and so forth. So when switch receives the packet, it needs to have a sum table to maintain the information that B prime is on port 5, and that is what is called a switch MAC table or a switch forwarding table. So a switch basically maintains a switch table which primarily contains three fields: the MAC address of the host, the port number onto which is connected, and the time how long it knows that the host is connected. So very similar to a forwarding table which we have seen in a router, but in the router's forwarding table, it used to be IP networks. And the next hop here, we just have the MAC address and physical port connectivity, and that is what it does. Now, the switches are called self-learning switches, and that means we need to see the how does self-learning work. That means how does the switch knows the hosts are connected. If you look at the routers, either they run routing protocol like what we have seen, the link state routing, which they talk to each other, the router get the information of reachability and build their routing table. Switches do not communicate per se with other switch. They just, when a host transmits, they looks at the packet and builds its own switch table or MAC table, and that is what we call as a self-learning approach. That means switch learns when it sees the packet where the host connectivity is. So let's take a simple example that host A need to send a packet to A prime. So A prime is the destination address, A is the source address. It will put its own source MAC as A. It will put destination MAC as A prime and send the packet which will be goes to the switch. Now when this packet comes to the switch, switch looks at the source MAC address A. Switch knows that this packet has come on port number 1. So by knowing that on port number 1 I received a packet with MAC address of A, so it builds it, adds this address into the table saying MAC address of A is connected on interface 1 or port 1, and whatever time to live, that when I received it. And that's how it builds its switch table. So every time switch receives a packet, it looks at the source MAC address, and if the entry is not there, it will make an entry. If entry was already there, it will refresh the time, or if it was connected to a different port, it will update the table. So by looking at the packet, switch builds its own table, and that is what is called self-learning switches, and that's how the switch primarily works. But how does it forward? So a simple algorithm, when a switch receives the frame, it first looks at the MAC address of the sending host and makes a new entry or update the existing entry into the switch table. Then it looks at the destination MAC address, find out the port onto which the destination MAC is connected. It is possible that destination MAC is not there in the table or it is there in the table. If the destination MAC is in the table and it points to the same interface and same port number, then switch will not do anything, simply drop the packet. If destination MAC is on a different port, then it will send the packet to the respective port. If, however, it does not find any entry for a destination MAC address, then it does what is called flooding. That means it forwards this packet to all the other interfaces other than the one onto which it receives it. So let's look at diagrammatically how does it work. Consider, for example, A needs to send a packet to A prime. So host A puts destination MAC address A prime, source MAC address A, and send the packet. Assuming everything is powered up afresh, that means when you switch powers on, its table is completely empty. When this switch receives the packet, it looks at the source MAC address, which is A, coming on interface 1, and makes an entry MAC address A, interface 1, and how long this packet has come, or how long this packet, the entry should be there. Now it looks at the destination MAC, which is A prime. Now A prime entry is not there at all. When entry A prime is not there at all, it will flood this packet on all other interfaces 2, 3, 4, 5, 6. So let me repeat again. A sends a packet to A prime. Initially, MAC table was empty. When it receives the packet, it makes an entry. Now it looks at the destination MAC A prime, which is not there in the MAC table. So it will forward this frame to all other ports other than the port 1. So it will send forward this packet to port 2, port 3, port 4, port 5, and port 6. And that is what basically called flooding. And that means this packet, if switch is empty, would be received by every host in the network. As we have seen that each host to receive the packet, the NIC card or the link level driver looks at the packet, look at the destination MAC and see it is mine or not. So each one of those NIC card will discard the packet except the A prime. When A prime receives the packet, it knows packet was for me. If I need to respond back to A, it will create a packet with destination MAC of A, source MAC of A prime and send it back. Now when switch receives it, it knows that A prime is connected on port 4. So it will make an entry for A prime that on port 4. And now it looks at destination address A, which is already in the table, which is connected to interface 1. So it will simply send forward this packet on the interface 1 and will not send to all others. And that is how the self-learning works. So let me repeat. If switch receives a packet, it looks at the source MAC address. If there is no entry for that MAC, it makes an entry. If there is an entry existing, it updates that entry. Then it looks at the destination MAC, looks for the entry. If entry is found, forward the packet onto that interface, assuming not on the same interface. And if there is no entry, it forwards that packet on all other ports, and that is how the switch forwarding works. Let's say we have looked at the switch which has only 6 ports and you want to connect more hosts, then switches can be connected to each other like we connect the host. So this is a simple case of number of switches getting connected. So we have a switch 4, switch S1 connected to switch 4, switch S2 connected to switch 4, switch S3 connected to switch 4, and that's how all these switches are connected. And now we look at the case how does the packet forwarding occurs when a machine A, for example, sends a packet to machine G or whatever mechanism. Now let's say machine A need to send a packet to machine G. How does whole thing would work out? We'll work out an example, but assuming that initially all these switches are just powered up, so none of the switch would have any entry in their MAC table. When A sends a Ethernet packet, switch S1 will receive it. It will record that A is on this interface, makes an entry, and since there is no entry for G, it will send this frame to both BC and S4. S4 again has no entry for G, so it will forward it again to both S2 and S3, and S4 also will seize that MAC address A. I received the packet on the incoming interface, it will record in its MAC table. So let me explain with a better example than you understand. Consider this case where I indicated the interface number. So we'll look at the switch table for the each switch and how they would work out. So I have a switch S1, switch S2, switch S3, switch S4, and initially their MAC tables are all empty. Now we'll take different cases and see how does it work. And this is important to understand that the way these tables are built and they are used. So let's consider host C sends a frame to host H. When C sends a frame, initially all MAC tables are empty. The frame would be received by switch S1. That means S1 would learn that C is connected on port 4 and it will make an entry in his MAC table saying C is connected on port 4. Now destination is H. There is no entry for the H in the switch S1 MAC table. So it will send this frame all other ports. That means switch 1 will send this port to the packet to A. It will forward the packet to B as well as to the S4. So packet would be received by both A and B as well as switch S4. When switch S4 receives the packet, it looks at the source MAC address which corresponds to C and it came on the interface 1. So it makes an entry that MAC address C belongs to interface 1. Switch S4 does not know whether it's connected to switch 1 or to the host. As far as it's concerned, it's just connected using Ethernet. Now when S1 receives the packet, it makes an entry. Now it looks at the destination MAC, which is H, and find there is no entry for the destination MAC address H. So it will forward this frame to both switch 2 and switch 3. Now when switch 2 receives the packet, same logic, it looks at the source MAC, which is C, so it comes on interface 1, so makes an entry that machine C belongs to or comes on interface 1. And now the switch 1 looks at the destination MAC, which is H, the entry is not there, so it will send this frame to all other ports other than what it received. Because it received on port 1, so it will send this frame to D, E, and F, all three of them. Of course, when D, E, F receives the frame, the destination MAC is H, which is not theirs, they'll all discard the frame. Same way, when S3 receives the same packet, S3 looks at source MAC, which corresponds to C, so it says C belongs to interface 1, it makes an entry. Again, S3, there is no entry for destination MAC H, so it will forward this frame to both interface 2, 3, and 4. That means this frame would go to both G, H, and I, all three of them. They will receive the packet. And that's how entry will be. Now let's say H has to respond back. H responds back to C. When H responds back to C, H is connected to S3. H doesn't know I'm connected to S3 or S4 or S1. It knows I'm connected only to switch. Switch S sends the packet. S3 receives it. Now S3 receives it, it looks at the source MAC and says, oh, host H is connected to interface 3. So it makes an entry for MAC address of H belonging to port 3. And that is what it does. And because it knows that destination MAC is C and it already had an entry for C. So it will forward the frame only on interface 1. It will not send this frame to G and I. So when H responds, G and I do not receive the packet. Now this packet goes to S4. S4 looks at the source MAC address, which is H. So it knows, oh, host H is connected on interface 3. So it makes an entry for interface 3. And it is looking at only, now it looks at the destination MAC, which is C, and S4 knows C is on port 1. So S4 will send this packet S2C on port 1. It will not send onto S2. This packet comes in, comes to switch S1. S1 learns, look at the source MAC H, come on port 1. So it makes an entry in port 1. And it already knows the destination MAC is C. It will send the packet to C. So the response S2C will not be seen by A and B, would not be seen by G and I, and S2 doesn't even know where the H is because it has not seen this packet. Now consider that the D sends to H. Now D sends to H, this switch S2 would receive it. S2 look at the source MAC. It sees that it is on port 2. So it makes an entry that D is connected on port 2. Now look at the destination MAC. Destination MAC is H and H2 has no information in his MAC table about the H. That means it will forward this packet to E, F as well as port 1 which goes to S4. So packet would be received by both E and F and it will go to S4. When S4 receives the packet, it knows that it has received and source MAC is D which is coming interface 2. So it will make an entry for MAC D and interface 2. And now because switch S4 knows H is on interface 3, so it will send this packet to on the interface 3 to S1. This packet would not go to switch S1 at all. And now S3 would receive that packet. It will look at the source MAC, which is D. So it makes an entry that D belongs to interface 1. It makes an entry, and because already has an entry for host H on port 3, it will send this packet to H, and G and I would not receive that packet. And so S1 does not receive the packet, and neither both G and I receive the packet, and that's how the switch table works. So I would like you to take a pause, look at it, try some other packet. Let's say if A sends to E or B sends to E, work it out. How does that work out? Consolidate, and we'll resume that in a short while. Once you have ponder over it, make sure you understand, go over it again, see that, and then we will look at later on how if I do multiple connectivity, the switch is connected like in a loop, what happens, that we'll consider next.